The next guest on my podcast is from possibly the coolest company in the entire region around here. If you haven't heard of them already, I strongly suggest you get your phone out right now and do a quick Google. So Vic Terry is joining me from Vertical Aerospace, who basically make flying cars. They are very, very cool electric vehicles that get a few people from one place to another. Look them up and you'll hear more shortly, but this is possibly the thing that I have been the most geeky enthusiastic about in the whole of the Giant Mind series. So I really welcome you to sit back and tune in and enjoy this one. Vic, thank you very much for joining us. It's great to have you on the Giant Minds. You are now officially a Giant Mind.
Oh my goodness. How ironic, because I've got a really tiny head.
We'll get into what you do and the company in a minute, because that's quite cool. But before we go there, do you want to start off by just telling us a little bit about your personal journey, kind of how you've got to be involved in the stuff you're involved with now, that sort of side of things?
Yeah, sure. So I'll start with my degree. If you've got a degree in rocket science, you've kind of got to say, hey, I'm a rocket scientist. So I studied at Bath, just down the road. Electronics with space science and technology, moved into electronics, quite liked broader product aspects, so ended up moving into systems engineering, then systems of systems, so really big systems. Moved around all over the place, whether it was consumer electronics, whether it was defense, aerospace, but really got into the whole software-driven paradigm and all of the innovations that have come out of Silicon Valley and software engineering. So that led me to where I am now, because I left aerospace the first time. I work in aerospace, for those aren't aware. We'll get onto that. But I saw this as an opportunity to bring all the stuff that I'd learned from the consumer electronics sector and bring that to the slow-paced world of aerospace.
Cool. Okay. And this year you won an award for being the best technology leader in the Southwest, which I was up for. So no hard feelings. Tell us about your leadership journey and where that started. When did you kind of move from the sort of more being involved in the engineering to becoming more of a leader?
I think it's been a bit of a theme throughout my career, actually, looking back. So systems engineering, you're kind of gluing a lot of the bits of the puzzle together, and you have to have that more holistic mind. You end up doing a lot of that PM, project management, program management type skills. It brings the communication skills together. So that was really the training wheels, if you will. And then as I progressed through my career, I seemed to be quite good at those things. So I ended up joining Vertical as their first engineering manager, and then scaling that up through to being a director, looking over 7 teams.
Great. And how would you describe your leadership style? What do you focus on the most? What do you care about?
I get asked this a lot, and it's a really simple answer: inspiration. So for me, as a leader, sure, there's loads of the smaller aspect or the key aspects of a leader, but for me, the top one that I pride myself on is being able to inspire folks. So I get a real kick out of, let's say you've got an idea or you're trying to pitch a concept or a way of doing things, bringing people along with you, inspiring them behind that vision, getting them really on board, fired up to do it. And then you walk away, you come back a couple of months later, and they're living and breathing it. They're pitching it to other folks because they've really taken those concepts to heart. And it's really cool when you start hearing your words coming out of their mouth, like trying to convince others and sort of bring more people along on the journey, whatever you're trying to achieve.
Yeah, I mean, I guess lots of people say it's all about sort of creating a definition of good and describing the goals and the objectives and kind of where we're heading. But I think that's a nicer way of putting it. It's because if you get them to the point where they're just so excited about those things, then everything else just kind of flows, I guess.
Yeah, indeed.
Yeah, brilliant.
The feelings, the mind, the feelings and the heart take over. Yeah. And then the mind follows. And much like you at Geiston, we hire some fantastic minds, like people who just can solve problems. So you get those guys fired up, guys and girls, point them in a direction, and oh my God. Yeah. It's, I don't know about you, but I often find that when I set them on a direction, what comes back is so much better than what I had originally had in my mind.
Great. So when you're recruiting and bringing people onto the team, what are the things you're looking for in those people to kind of to take that forward?
It really depends, because there's no one size fits all for what you're recruiting for. Where is the hole in the team that you're trying to fill? So actually one of the things that I've found along the way is, and I'm sure other folks have too, is if you fill up a team with rock stars, you're going to have problems. If you don't put rock stars into the team, you're going to have problems. So you need that balance of those ambitious rock stars and the steady eddies to kind of balance it all out and actually get what you're trying to achieve done. But coming back to things, qualities that I look for, adaptable. The modern world is changing quicker than most of us can keep up with. So you've got to have that mental aptitude to be able to take on new thoughts, ideas, run with it. Work from first principles. A lot of the stuff that we do, the closer you get to kind of deep tech, no one's done this before. There's no one to just turn around and say, oh, how did you do this last time? Because there was no last time. So usually probing around those sorts of skills and qualities.
Yeah, and I guess the vertical journey is one of sort of from startup to scale, and the adaptability is so important to follow that route through, right? You need people who can initially probably wear loads and loads of hats, but have the ability to dive deep into certain areas as well.
Yeah, indeed. There's, I guess if you zoom out, most startups will take a similar sort of journey. As you say that, you've got to wear multi-hats. The stepping up the organization, now there's lots more people, you can't do quite as much, so you end up going deeper. Moving from, and then on the other dimension, moving from technology demonstration, prototyping to productionization. The two polar opposites of mindset. So one of my observations is that the people you need at the beginning are not necessarily the people that you need in the middle, they're not necessarily the people that you need at the end. So having an idea of where folks sit in terms of their skill sets, can they go the whole journey? Yes, absolutely, some people can. And that's why they got into it, because they want to get to that end. They've had the experience of productionization, but they want to start and build a way through to that. And others are just creatives, people who can solve some really, really crazy problems or be really, really innovative. But as soon as you try and put them in a box, in a big organization, there's no point.
Stable production line, just switch them off, basically.
Yeah, exactly. They're not getting anything out of it. You're not getting the best out of them. So, I think also in your hiring, especially if you're a scale-up or on a scaling journey, then take into account those things in your hiring process. I'd certainly recommend thinking about.
Yeah, definitely. Right, so let's get into the exciting stuff, Vertical. You joined fairly early on in the Vertical journey, right?
I did, yes. So employee number 8. Ironically, that was 8 years ago now, almost to the month, I think. So 8 years ago, we're now an employee number 8. We're now over 400, listed on the New York Stock Exchange. We listed at a valuation of 2.2 billion US, which is pretty crazy. We've got
a punchy IPO. Yeah.
Well, we did it through when, if you've heard of a SPAC, back when SPACs were called, like very odd financial instrument. Effectively, a vanilla company gets listed, and let's say to list on a stock exchange, you have to jump through 20 hoops, say 20 steps along the journey. So this vanilla company gets listed, which is basically just a pot of money. They then find someone to acquire and do what's known as a reverse merger. So we were then acquired by that, which was effectively the investment, the pot that was sitting there. And then the name changes. And to do that, there's only, say, I'm making up the numbers, but order of magnitude, 20 steps to list, but to do the reverse merger is like 8 steps.
Right.
So it's a quicker route to IPO and getting the level of capital that doing something like Vertical Aerospace needs.
Yeah, it takes quite a lot of money to build a flying car.
Yeah, fair amount. The US folks are spending it like it's going out of fashion. We've been a little bit more conservative and with our cash and been very, very diligent with it. That's caused pain points along the way, as you can imagine. But still, it's 100 million a year run rate. Yeah. When you're not bringing anything in, you know, you've got to have investors with who buy into that vision. deep pockets, strong stomachs. There's going to be some bumps and twists along the way to get there, for sure. Yeah. But we already have validation. We're really close to our customers. We've got something like 5.4 billion US in pre-sales of aircraft. Like the first 4 years of production or something like that is already allocated.
That's amazing.
So the demand is there. We've just got to do the trivial bit of making it all work, certifying it to the highest level of safety standards in the industry today.
Yeah.
There's the safety standards that we enjoy when we jump on a Boeing or an Airbus to go on a holiday.
Yeah, yeah. And just for those that don't know much about Vertical, let's just sort of go back to first principles. Is it a helicopter? Is it a plane? Is it a car?
I always just say it's a flying taxi. That normally gets a reaction from folks. But when you look at it, it kind of, as you say, when you squint, it looks a bit like a helicopter. It looks a bit like a plane. But yeah, it's both of those. But no, it's neither of those. So fully electric, vertical takeoff and landing, transitioning aircraft. So what does that mean? Let's unpack that a little bit. So taking the technology from drones, so multi-rotors today. We have a few more of them than 4 for safety reasons. So that gives you your vertical lift. We then transition onto the wing. So the front propellers that were sticking up to lift you up now start to come down 90 degrees and poke forward to then pull you along like a conventional aircraft on the wing.
Yeah, and the back propellers fold up.
And the back propellers, turn off, fold up.
Yeah.
And sit in the airstream.
Yeah. And has anyone done that before?
Looking back at the history of it's pretty mad. So the history of aviation, there's been some smart folks, right, looking at this for decades, but they've not necessarily had the technology to do this. So we actually found some, I can't remember who it is now, maybe you could put it in post.
Okay.
Someone had done all of this using gas turbines and hydraulics and linkages to try and do a vertical takeoff, stabilization, multi-rotor, and without the use of modern computers and control systems. So it's humans just pulling all these things. Hats off to them.
To be on board
I don't think they got it to fully work, but there are other people in this, other folks in this space. So the big ones in the US are Joby and Archer. Our aircraft looks very similar to the Archer aircraft in terms of its general configuration. Joby's is a bit more squished and they transition slightly differently. And we've just seen a bit of a shakeout in the industry as well. So 2 German companies, Volocopter and Lilium, again, 2 completely different configurations again. So one was more of your traditional just a multi-rotor, no wing. That was the Volocopter. And then the other one was a ducted fan. So it had lots and lots of fans all in the wing and the whole wing tilted.
Right.
So yeah, those, there's been a bit of a shake-up. So those guys folded at the end of last year. So it's now mostly us in the US.
Some cleaner space for you to fly into. So
indeed.
Yeah. And how's that evolution happened in practice? So we were talking before, there's the differences between simulation, between using scale models and the real thing. So how do you kind of progress between those different modes? Yeah,
absolutely. So as we touched on employee number 8, you haven't got much at your disposal when you're 10 folks in a shed, right? So you have the choice of, do I do everything in simulation, then validate that simulation and then go to full scale? Or do I do subscale first, find out all the issues and then go to large scale? And the answer was different depending on which part of the life cycle we were as a company. So when you're only a couple of folks in a shed, then it's easier just to build and break stuff. We had a whole wall covered in like snap carbon fiber rods, propellers that are, the propeller blades that we'd snapped until it got a bit silly and we just had to take it all down because there was too many. But then you need to understand the translation of how does that scale, subscale, translate to full scale. So we actually got really good at understanding those differences. We put little bits of software, for example, between the flight control computer and the propellers to give them the dynamics of the much larger aircraft. So we could do all of our tuning of all the control systems at subscale, then literally lift the flight control computer off, put it onto the full scale, and it flew beautifully. Honestly, wow. I think there was like one minor bit of tuning that we needed to do afterwards. But
that's amazing.
Full scale, you have the risks. Obviously, there's a lot of energy and effort and capital that goes into doing something at full scale. And that kind of ends up why, as the business scales and you can hire more people to dedicate towards simulation, that is a better route to take. So rather than doing the subscale.
So simulation's more expensive or slower than subscale? What are the kind of differences?
Once you've got a sim, you can do a billion runs in the cloud if you need to. You can put your pilots in the in the pilot in the loop simulator, and they can fly the dynamics and put your VR headsets on and all of that.
So you've got this really slow period of creating the sim, and then you very, very rapid iterations.
Yes.
Compared to a much more steady.
Well, you say slow period creating the sim, so it depends on what you're trying to understand, what you're trying to validate. So we could have quite a simple, lower fidelity model to understand some characteristics. And then as the program evolves, you put more fidelity in the simulation, you swap it in and out.
Okay.
But we did have the decision point of, do we continue doing the subscale testing? Because we got pretty good at that. However, when you start putting the types of systems that you want on there, slowly the scale creeps up. And at that point, you're like, well, now it's very expensive to build and operate. It takes a lot longer than your little toy drone that's basically held together with gaffer tape. At which point, you might as well build a big one. So the case then writes itself to go headlong into sim.
Yeah, well, just because there's so many different components and so much electronics attached to it.
Yeah, and the size and weight of those then drive the overall scaling that you can achieve. And sim is always the way to go for this sort of stuff anyway. It was more the trade-offs that we had at the time of what is the fastest route to get a demonstrator in the air to raise the next round of capital. So in the startup world, you're always battling that kind of what's the quote unquote right way to do it, and then what's the way that we need to do it.
Yeah. And you've got all sorts of capital milestones that happen that are really important sort of fundraising moments, but also really important technological moments, right, where you actually breach sort of certain barriers that are kind of proving the point.
Yeah, indeed.
And you've hit a couple relatively recently of like full-scale flight.
Yep. Yeah, so hover testing we achieved quite quickly. I refer to that as low energy testing. Ironically, it's the hardest the batteries ever work. You're deploying about 1.3 megawatts of power out of these things. So we're talking about a huge amount of energy that gets delivered. But in terms of the momentum of the aircraft, you're just hovering and moving around at, say, 20 to 40 knots, which is very different to being above the Cotswolds flying at 150 knots. If something goes wrong there, then it goes wrong very quickly and very, very badly indeed. So there's obviously a lot of steps and rigor that we need to go through to transition between those two different regimes of test. So just recently, we've done the wing-borne trial, so that was really good to see. After so long in an aerospace company, it was the first time I've ever been part of a wing-borne flight, a conventional flight. All the stuff I've done before is all
so that was taking off from the ground on a runway.
Yeah,
just like
any normal, like a grown-up plane. So conventional takeoff onto the wing. We first did what's called stick to surface, or direct mode is what we term it internally. So that was basically the controls are wired up to directly control the surfaces. So
when you say wired up, they're still fly-by-wire, right?
Still fly-by-wire, but it's basically emulating the olden days where it really is fly-by rods and levers. The pilot then has full control. We can shake down these new systems that had never been flight proven before. Obviously been proven by their manufacturers, but altogether, our whole aircraft. Then just recently we then closed the loop on that. So all of our aircraft is fly-by-wire. You can take your hands off the stick and the aircraft will continue to operate safely. So in order to do that, you have to have a lot of work goes into the tuning and the all the fail-safe mechanisms of those systems. So turning it over to turning on that full control system was a nice big moment. Obviously, it went off without a hitch. We do a lot of testing, a lot of planning. So
great.
To be expected, really.
Yeah, and,
we also
so that
hit
wing-borne
another
flight has happened now completely on that. Yeah. On that
yeah. So now that we've done the vertical takeoff and landing, we've done the CTOL, conventional takeoff and landing. We've now got to join those two bits together. So take off vertically, transition onto the wing, fly conventionally, transition back, and land vertically again. So complete the whole mission.
And there's technical challenges associated with that, but there's also legal, like restrictive challenges, regulatory challenges that are associated with that.
Yeah, so we don't enjoy some of the luxuries that, say, the folks in the US have. They can go out in a desert, they've got a load of space. We've got the Cotswolds with schools and hospitals and things and people's houses underneath. But also the rules around prototype aircraft are slightly different as well. So in the US, the inspector comes out and does some minimal checks and assures himself that it's okay, gives them the stamp, go away and fly in the desert in Utah or whatever it is. In the UK, we actually run through effectively a mini certification program. So we have to go through all the rigor of having our requirements workflow all the way through to verification, producing all the evidence to the authority, then reviewing that. Now, clearly we've lowered the bar because it's not putting the general public on board, and it's a professional test pilot, and these are by definition unproven systems, and our job is to prove it. So we lower the bars, but it's still the same process and workflow. So it feels a bit slow to begin with when you compare it to some of the luxuries that other companies enjoy. But actually, when you zoom out, our organization is now battle fit for a certification program. We now understand the rules and processes that we need to adapt from going. I spoke earlier about going from the demonstration world to the production world, the types of certification. That's what we're doing right now, effectively. But also building trust. So your counterpart on the CAAs, in the UK it's the CAA, we'll also be going through EASA and a lot of the other regulators as well, which we have full engagements with them already. But building that trust, that rapport, because ultimately the person on the other side is signing off on public safety. There's a lot of weight on their shoulders, especially when we're talking about new and novel technologies and flight regimes that just haven't really been done before. At this
and you can bet the tabloids will be all over it if something goes wrong.
Yeah, exactly. So everyone, everyone's laser sharp, laser focused on this. We need to take risk. Everything is a balance of risk. And there is no rule book. When you're talking about certification, there's a rule book that you follow. Here's the rules. Here's all the lessons learned over the years. Follow them, and things will be okay. We haven't got that because, by definition, we're venturing out into the unknown in some of these things.
You're sort of making the rule book as you go.
Not quite. There's a lot that we can borrow from, but there's little oddities, little edge cases that pop up that you just have to work through. So getting that rapport with the person on the other side, so they say, okay, no, I trust you. I don't need to dig any further than that. That then is going to pay dividends when we get to certification, because there is that knowledge of where does competency end, where do we need to sort of bolster things.
And right now on that journey, this might be out of date by the time this podcast gets broadcast. But right now, where are you?
On certification
on the transition.
On the transition, yes. So as I say, we've completed both sides. We now have 2 jobs to do simultaneously, and it will depend on weather conditions or which bits of paperwork get released first. But so the 2 jobs we need to do is attack it from both ends. So from the hover, get faster and faster and faster, and back off, faster and then back off. analyze the data and sort of get close to that transition point. And then from the wingborne, the same thing. So get slower and slower and then speed up, slower and slower and speed up, and get those data points so we get closer and closer to those two speed ranges. One of the complex things with transition is basically aerodynamically all hell breaks loose. So as the rotors at the front start to come forward, hopefully you can visualize this in your mind's eye. Think of the wing on the front. You've got two rotors on the front and back. The front ones are tilting, but all of them are still spinning. So we've now got airflow getting ingested on a rotor that's edgewise, so not directly in the flow, but kind of at an angle, and changing. That's sucking in air, creating a turbulence. That turbulence is then getting blown over the wing and then re-ingested by the rear rotor that's still spinning. So the complexity of the aerodynamics is pretty crazy.
Yeah.
We've run obviously lots and lots of simulations. We kind of know what should happen, but until you go and do it in the real world with crosswinds and the odd bit of rain here in the UK.
Yeah, I mean, fluid dynamics is inherently hard,
Yes.
just on its basic level, right? And
Yeah.
you're really turning up the dial on that. I guess the loads of the rotors as they're moving through their path must be radically changing and so on.
Yeah, indeed. Yes. Yeah, the loads and how that transmits. And are you at the front end of the sweep or the back end of the sweep? So you can get different vibrations, which then come through. And
is that, presumably that makes this a very different challenge to the competitors who move the whole wing up and down?
Yes. Yeah. Well, there was only one of those, and they are no more.
Right. So even those different challenges, smoother path probably, hopefully.
Yes.
Amazing. And so it's interesting. You're kind of like traveling the road from both ends, and you've got to meet somewhere in the middle.
Got to meet it in the middle.
Yeah.
I don't know
Feels
whether
like digging the Channel Tunnel.
Yeah. So to extend that analogy, I don't know yet whether it's going to be best to start from France and travel to England, or start from England and travel to France. So do we start from a hover and get onto the wing, or do you start from the wing and get into the hover? There's pros and cons of both of those.
Yeah. And I guess like just from my limited knowledge about planes, you come into stall speeds and things because the wing will stop working aerodynamically in the same way.
Yes,
as it
indeed.
At some point, right?
Indeed. The flight control laws and the way the platform's set up, obviously physics still is at play. Yes, there is still a stall speed, but ultimately you're still generating lift. So the way the flight control computer works is we actually use a thing called nonlinear dynamic inversion. So some big scary words. Rather than using conventional control theory, which is basically just minimizing an error of command versus output, what we actually do is embed all the physics of the aircraft inside the control loops themselves. But we invert that physics. So with our physics equations, we know if I put this input, I get that output. If I invert those equations, I want this output, what inputs do I need to give? So do I need more tilt? Do I need more speed on a rotor? Do I need more deflection on a surface, etc.? So in using a lot of those inbuilt mechanisms, the output of the control laws is, here's a list of all the things you can do to achieve that. So I can rely more on my wing, I can rely more on my rotors to achieve what I'm trying to achieve, that lift. Right. So the kind of stall speed is more like the technical point of where do we move from majority getting generated by the wing, majority generated by the rotors. Rotors, propellers, there's a whole subreddit argument on
which they are.
what they are. Yeah, I'm not,
right.
I'm not going to get into that one.
Yeah, no definitive answer, I guess.
But why do I talk about all of that? Because from a pilot perspective, you don't care.
Right.
The aircraft just does whatever it needs to do in that situation because it has knowledge of the physics.
So from a pilot's perspective, it's basically like forwards, backwards, up and down sort of type thing.
Yeah, that's the beauty of it. So even me, a non-pilot, a numpty, if you will, could sit in this and fly it perfectly safely.
Yeah.
So it's very intuitive. You just say, I want forward or more forward, left or more left. And then depending on what regime of flight you're in, the flight control computer just takes care of it. Because if you think, if I want to go forward on when you're in vertical mode, you actually have to pivot the whole aircraft forward, much like a helicopter's disc, to move forward. Whereas when you're in conventional flight, you need more throttle.
Yeah.
So it'll take care of all of that for you.
Wow. Yeah.
And as I said earlier, it's fully stabilized, so it just returns to you. Command a you sort of, it changes. I won't get into that bit, but yeah, you can hands off the stick, and it will just continue doing what it was doing. So if that was hovering, it will just hover. If it's maintaining a speed, flat and level flight, it will just continue to do that.
Yeah. And the electric side of it, what are the big external impacts of that? Noise presumably is one.
Yeah, so I guess the question I often get asked is, why not just use a helicopter? So there's the green credentials, with it just being battery. We all know that batteries have limitations, otherwise we'd all be driving electric cars right now and there wouldn't be a gasoline cars. But with that, gets a load of advantages as well. So I spoke about the ease of control. I now have a flight control system that most helicopters do not, just by pure necessity of needing it. So now inherently, I can put all the envelope protection, I can put a lot of safety features in. I've used the term multi-rotor a few times. We have multiple rotors rather than one single rotor. So that gives us some redundancy, but also the sheer physics of it makes the whole aircraft so much quieter. I think I can't remember the number now. Oh my goodness, I think we quote something like 10 times quieter than a conventional helicopter. Right. So why is that? What's driving that? So loosely speaking, half the noise of a helicopter is the gas turbine engine. Well, we don't have one of those, we've got battery, so that's half already gone. And the other half of it is as the propellers are going round, as the rotor's going round, the tips of those rotors are actually going supersonic on a helicopter. So that's why you hear the thud, 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 thud. It's a sonic boom every time those go round. Because we've got lots of rotors and they're smaller, the tips are spinning a lot slower just by the pure physics of it. So actually we don't have that sonic boom. So there's two major drivers of noise already taken out. Now, why is that useful? Folks don't like sitting under flight paths anyway, because aircraft are quite noisy, so we all understand that. But what does that drive? That actually drives a lot of the economics and how close into a city, and therefore how useful these products can be. So take Battersea Airport in London, for example. They are heavily restricted on the amount of flights they can have a day, purely on noise pollution. Right. So if I take the crew multiplier that we had earlier, that means with our aircraft, I can do 10 times more flights than I could with a conventional helicopter into the centre of London.
Mm-hmm. Yeah, that's a big advantage. And presumably there's a carbon efficiency sort of gain as well. Like even if you were producing the electricity from fossil fuels, it would presumably still be quite a lot more efficient.
So yeah, there's the efficiency piece, but there's also the maintenance piece. So with a helicopter, we hear a lot more about helicopter crashes, right, than we do of conventional aircraft crashes. And one of the principal drivers is just the way these things are made up. So there's a gearbox that runs to the tail rotor. If you lose the tail rotor, there's a jam in the gearbox or damage or what have you. You're pretty much, that's it, game over. So there's a lot of money that goes into the maintenance of those components. There's a lot of money that goes into the maintenance of something as complex as a gas turbine engine. They're really highly tuned devices.
And just so many more moving parts.
Exactly, yeah, moving parts, they wear out. Electrical motor, I've got two bearings. I've got a rotor and a stator, and the tolerance of all of that isn't actually all that crazy when you compare it to something like a gas turbine. Yeah. And then the battery is a battery, I just replace that as required.
Yeah. And so in all this testing and movement through the whole process, you're generating quite a lot of data.
Yes, we generate phenomenal amounts of data. So there's the aircraft itself. To run a flight test, it's quite a precious thing. So we want to make the absolute most out of every single flight hour, flight minute that we can. So the aircraft is highly instrumented. We generate, well, depending on the flight, it's something like 30 gigs of data that we get. That's pure time series data. That's not all the video stuff as well that we capture. That's just pure streams of time series. So there's a metric internally that we use called time to graph. So how quickly can I get all this volume of data off the aircraft, put it in front of an engineer, draw a graph, so they can go good graph, bad graph, and make a decision and move on quickly. So in days gone by of flight test, we've got to take memory cards out of like 3 different things, and someone's got to upload them to a network drive and all of that. We've replaced all of that with software automation, data pipelines in the cloud, and all that good, and databases in the cloud and all that good stuff. So what would conventionally in days gone by would be a week before you got your hands on the data, our time to graph metric is about 20 minutes.
Wow. Okay.
So there's huge volumes that need to move across. Take that design pattern and then apply that to all the rigs as well. So for every aircraft we've got, there's probably 20 rigs, say, that are running testing, whether that's pilot in the loop, where you've got a lot of systems all together, or the Iron Bird type rigs, we call it Vital, or whether it's component rigs as well. All of those need to. It's all about getting data into the hands of folks to turn that into information, to turn that into decisions, to move the business forward.
Yeah. So I guess the crucial thing about that moving from weeks to 20 minutes is you can then run several flight tests in a day back to back, even like tweaking things in between.
Yeah, indeed. Absolutely. And we actually got our very first, you spoke about milestones earlier. We've been trying for a while, but lots of things come into play, whether it's the weather here in the UK or things that we find. We've been trying to get multiple flights in a day. And last month we achieved our first one of those. So it was a big celebration internally for that.
Yeah. And all the flights are out of Kemble in the Cotswolds, aren't they?
Yes, indeed.
Yeah. And how's the business move from Bristol to Kemble? How does that sort of 2-site thing work?
Yeah. So in the first prototypes we did a long time ago, we used Kemble Airfield, and it was just a handful of us, and we sort of drove back and forth. The second one, we actually set ourselves up at Lambeda. So we in basically as far West Wales as you can get, Northwest Wales, away from as many folks as possible, which meant we had to deploy a load of guys there, and then it was quite difficult with the 2 sites being so far apart.
Yeah. Especially it takes a long time to drive to there as well, doesn't it?
Yeah, indeed.
It's not that far on the map.
4-hour drive or something like that. So for these aircraft, we were dead keen on having a base as close as possible, especially where the company has grown, and it's not just the engineers are being the technicians, the assemblers, the fixers, all of that. We've got distinct roles now. So the build and maintenance facilities being in reasonable driving distance to engineering was an absolute must. So we split ourselves up over a few sites now. So we've started in HQ in Bristol. We've got the battery centre out in Avonmouth. It was quite tricky to find a facility that had big enough cables coming in from the grid.
Right.
I think someone said there was only like 2 of them in the local area that had that much, or that could cope with the power demands that we required.
Yeah. Do you know what the number is for how many megawatts he needs? Probably quite.
Uber watts, whatever it is. Yeah. So over there they're doing self-cycling. So there's lots of, you charge and discharge the battery individual cells in many different characteristics, being varying temperature, humidity, current cycles, how much current you're pulling in and out, in order to create really good models, simulation models of those batteries. So that's a lot of the testing that goes over there, the shaker tables and other bits and pieces as well. We've then got, so the Bristol site is mostly the low power equipment. So a lot of the electronics, digital communications, a little bit on the low power actuators and low voltage actuators happens there. But then all the high power stuff. So we're talking about spinning rotors, so propeller blades, rotor blades. Sorry for whoever's got an argument either way on which one of those are. 700 volts spinning the motors as well. I don't know if you've ever had a shock from the mains 240. It tingles a bit. You've got to go sit down and have a coffee afterwards. But if you get hit by 700 volts, you don't get a chance to go.
And 700 volts DC, presumably.
DC as well, yeah. So super dangerous. So it needs a lot of protections around it. So that's we've got a facility just off airfield at Kemble, and then on the airfield we've got final assembly and maintenance and flight test.
So it takes a lot of people to make things a reality. So how do you decide what to do in-house and what to do externally with partners, and who do you have involved? How many? How do you manage that? How does that all work?
Yeah, great question. Building an aircraft as complex as this is a big endeavor, and as you say, it needs a lot of pieces to come together. So at Vertical, we took a decision pretty early on to be you're either going to be vertically integrated and do all of it yourself, or you're going to be the integrator. And we chose to be the integrator. So that means going out into the supply chain, finding out who's the best in the business, not just what they do, but also then cultural fit, because what we're doing is not traditional in aerospace. So we need partners and supply chain that also are happy to work in non-traditional ways, think differently, to solve some of the unique problems that get thrown up with the problems that we're trying to solve. So one of the key drivers is, am I going to get better from industry, or am I going to get better from doing it myself? So what is value add? And one of the key mantras that I used to make some of these decisions was, what is value add versus must have? If it's a must have, then I'm just going to get someone else to do it. Safety critical software is notoriously difficult, and you need pedigree behind you to get over some of the momentum, the certification momentum, to get there. So actually flight control was one of the very first things we said, no, we're going to outsource flight control systems and the flight control software, we partnered with Honeywell to do that. The flight control laws, that's a bit closer to home. That's how the aircraft flies. So we actually entered into a partnership model with Honeywell. So we use some of their flight control laws expertise and some of our own. Ultimately, it's got to end up at ones and zeros on the flight control computers. We looked across everything we do. Structures, we're going to go and buy that. Batteries, well, that's new and novel. That's value add. So we're going to become experts in that and keep that in-house. One of the other ones which might not be so obvious is propellers. We kept that in-house. So,
or rotors.
Or rotors, as per your persuasion. So there has been billions poured into rotor and propeller design over the decades in aerospace. So why on earth do we think that we can do better doing it ourselves? So we did. We went out into the market and we're like, hey, we need some prop rotors that look, see what I did there? we need some that look like this. And everyone we spoke to went, oh, that's a bit weird. Because if you think about it, these need to do several different jobs that aren't conventional jobs, because we've got lots of smaller ones. We've got ones that need to lift. We've got the ones that need to lift and cruise as well. So actually, the more we looked, the more we had the supply chain coming back saying, oh, well, we don't really know about all of that. So turns out we'd done a load of research ourselves anyway, and we got pretty good so that we could be intelligent customers, and decided, you know what, we've got the world-leading experts right on our door internally. Right. So that we decided to keep in-house. Yeah. So that's the design. Manufacture will obviously be outsourced.
Yeah, great.
But yeah, there are thousands upon thousands of components that need to get on dock at the right time to the right quality to actually build the aircraft. So the supply chain side of the organization needs to scale accordingly, and it's not quite, but almost as complex as some of the engineering challenges.
Yeah, I mean, I imagine the supply chain departments at somewhere like Airbus would be more than the size of Vertical at the moment. Yeah.
Well, yeah. Actually, when we signed with Honeywell, one of the observations I had is they have more lawyers than we have people, right, working through these contracts that we're about to enter into. So, yeah, there's a lot of who are those people that we're truly partnering with? Do they follow that same ethos? And that goes all the way through from the engineering mind solving the hard problems, all the way through the business to how do we actually want to run as a company? And we need to look at all of that in order to get these great partnerships to achieve what we need to achieve.
Yeah, amazing. So tell us a little bit about the future. We've talked about the next big milestone as being that transition.
Yep.
What beyond that? What happens from there?
So that demonstration proof point, as you say, that feeds a lot of data in. We spoke about the complexities around the modeling in that transition region. We have a pretty good idea of what it looks like, but we'd like to bring those error bars a bit so that we can optimize the designs that we have for the production aircraft. So if you squint a bit, the production aircraft looks pretty similar to the aircraft that we're doing now. Obviously, over the years, we've refined some of those details. We've learned a lot more from doing the prototype, so you can imagine it's changed a little bit. So we have what's called a type design. So aircraft are described as types. So we have pretty much the type design. We've done familiarization sessions with all of the major authorities globally on what that is. So that program is already marching on. There's those final refinements to come through from the demonstration phase, but we're full in that crossover point of workforce of being on demonstrator to certification. So we're right at that sort of equal crossover point where suddenly the floodgates are going to open, the whole business is going to transition, pardon the pun, over to the certification program, working with the partners that we've already got on board to try and get the types of aircraft built and start flight testing of that one. Yeah,
and there's a pilot certification program that probably needs to go because there's no such thing as a vertical pilot's license at the moment.
Indeed. When you're trailblazing like we are, you end up bumping into all these funny little bits that you're like, oh, I took that for granted in a previous role, or I didn't think that we need to solve the rest of the world's problems as well in order to bring this to bear. So pilots is one. Which license do you start from? And we're kind of coming down to, well, you can start from either. You can start from a helicopter license or a fixed wing license, and then get a type conversion onto ours. A lot of our customers actually are taking the concept of, is this aircraft a feeder for their junior pilots to get onto the big Airbuses or Boeings, the 777s, what have you.
Because it'll actually be easier to fly.
Yeah, they'll be easier to fly. They can get up their miles, get up their hours, etc., and then sort of a feeder onto their bigger fleet. Other things that we need to solve. Well, there are no vertiports out there at the minute. There are companies that we're in talks with. It's all public domain stuff. There's loads about out there who are looking at, well, what does a vertiport mean? What do I need there in terms of the charging infrastructure? Because now actually there's a lot of energy that I need to get there, much like a lot of the car charging places that we have today. There's actually batteries buried underneath the car parks so that they don't just overwhelm the grid every time you plug your battery, your car in. There's then airspace. So a lot of airspace today is driven by voice. You've got an air traffic controller. I found out the other day actually that the air traffic controllers in the Heathrow control tower, do you know how long their shift is?
Probably not very long.
You're wrong.
Because
15 minutes.
15?
They sit on 15 minutes managing you and me coming in on our flights, and our families all coming in on our flights. The workload is so intense that after 15 minutes, they're off shift, have a tea break, and rotate like that. Wow. So there's so much that's reliant on voice communications in these individuals. We need in order to get the densities up that really sort of allow this whole industry to take off, you need a paradigm shift there to move to digital communications, to humans on the loop or over the loop as opposed to in the loop. So we're working in projects like CESAR with the European community, Future Flight here in the UK with folks like NATS on how do you solve those problems as well.
Amazing. And who's going to be flying them? Like, is it going to be privately operated? Is it going to be a big consortium? You've got so many pre-orders. Where are they all from?
It's mostly airlines. So whether that is, say, American Airlines, and it's how do you get a feeder to the airport effectively? How do I get folks from out or in the main city into my major airport and up and away on their business flight or what have you? We do have leisure operators, tour operators that are quite interested. So
flight over the Grand Canyon sort of thing.
Yeah, indeed. People associated with hotel groups, so think of that sort of, instead of getting a coach, you get one of these aircraft to do that middle mile or maybe the last mile, depending on how that works out.
Okay, so I mean, there's so many potential applications.
Yeah,
and I want one, but I don't think I'm going to be on the list anytime soon.
Yeah, indeed.
Amazing. Well, thanks very much for joining us, Rick. That's been so super interesting. We could talk for hours
No
about
worries.
such a fascinating topic. Really appreciate you coming in. Thanks a lot.
Thank you.